high voltage, low current.
Yeah.
If we ever do this again, I might just have to invest in a squirt. I can go squirt Nelson next time.
That's right.
Just have it loaded. Look, and start spraying people.
All right, Michael's ready. Let's talk about components.
I'll just display all these unless.
Sure, sounds good. I'm actually surprised they start with ICs because that ICs combine many of these other base components, but that's all right. An integrated circuit is a little circuit that you might build on a board, but it's scaled down and is put into a small package. They might look like these, even this. This looks like a transistor, but it's actually a voltage regulator, so it truly is a little IC in itself. Various schematic components. All of the parts that we're going to talk about, they all have a symbol that we can use when we're trying to describe a circuit to someone. So I'll talk about schematics briefly. If I want to tell someone else how to build a radio, there's a way I can draw it out. So think of this as like a little recipe for a circuit. And all the components that you'll need are represented by different symbols on this drawing. And your book will tell you what the symbols are, but there's a lot of basic ones that you need to know. And from a practical standpoint, you can just go online and look them up. I will also say that there are different standards for symbols, especially US versus international standards. Like the book shows a little rectangular box for a fuse, but internationally, that usually represents a resistor. But once you look at a schematic long enough, you can usually tell what's what. In the United States, this little zigzaggy line is a resistor. But honestly, on international schematics, you'll see it. It's a little square box. So you have to keep that in mind. And even over the years, if you're looking at older drawings, it's not unusual for them to change how the symbol is drawn. But after a while, you can figure out what it is. Electrical symbols or schematics, they are theoretical in the sense that it tells you how the parts have to be hooked up. It does not necessarily tell you where they have to be laid out on the circuit board. Yeah, right. So once you actually implement a schematic by building a circuit, it's up to you to decide how to actually lay the parts out on the board.
Right.
And two people could build the same device, the same radio, the same circuit, and have it look totally different. Sometimes there are reasons why you'd want to have certain components together or apart, separated from each other. But beyond that, it really doesn't matter how they're laid out, as long as you want to find the layout that works best for connecting the components physically. So we'll start with resistors. Usually, resistance is bad. If in a wire, for instance, I would love this to have as low of resistance as possible because that's a problem in this part of the circuit. But sometimes we need resistors. Sometimes you need to limit how much current can flow through a circuit. And I'm careful on how I choose my words because resistors limit current, not voltage. Now, when there's actually current flowing through a circuit, the end result is you have a lower voltage. So even if you want to reduce the voltage, you have to do it by restricting the current flow. Now, there are ways to reduce the voltage and keep something at a constant voltage, but that's important to understand because let's say, I'm just going to grab a battery here because it's handy. Let's say that I need 1 volt for a circuit, and this battery has 1.5 volts at its terminal. So I take my multimeter, measure voltage, got 1.5 volts, but I need 1 volt. So let's say I do my math and I want a 1K resistor, 1,000 ohm resistor. So I take my 1,000 ohm resistor and I put it in series with the battery, and I put my positive lead here and my negative lead here. Well, what's wrong? I still have 1.5 volts. That's because there's no practical amount of current flowing through this circuit because the meter has a very high resistance. But once I put this in circuit, let's say maybe I have a light bulb hooked up through here, hook the light bulb up. Now I take my same measurement, I measure from negative here to this terminal on the resistor. Now I have my 1 volt because now there's actually current flowing through a circuit. Variable resistors are potentiometers, pots as they're often called. That's one common type of variable resistor. So inside this component is a resistive material in a circle. And there's a little tab, so as you turn this, you're moving further away or closer to one side of that potentiometer. This is a common one. It's probably a volume control. There's even little ones like this. I'd call this a trimmer. It's got a tiny little screw on the end. You'd probably bury that inside a circuit someplace so you can get it tuned or adjusted to exactly what you need. A couple examples. Capacitors store a tiny charge. They block the flow or restrict the flow of direct current, and they pass alternating current. And that's, from a practical standpoint, how we usually use capacitors, because you want to block direct current and allow alternating current to flow. Different values of capacitors will have different effects at various frequencies of alternating current. So if you're talking 60 hertz, 60 cycle current like you get from the wall outlet, that's vastly different than a transmitter operating at 146 megahertz, million hertz. And different capacitors will affect those frequencies differently. So maybe in a circuit, we're going to talk about tuned circuits in a few slides later, but maybe in a certain circuit, you want it to only pass VHF, very high frequency currents. So you'll find the right value of capacitors and inductors to tune the circuit to those frequencies. But they're real common for blocking direct current. Especially, I'm not going to touch on vacuum tube equipment a whole lot, but they're used a lot in vacuum tube equipment too. Capacitance is measured in farads. Sometimes bigger capacitors will be microfarads, smaller ones will be picofarads. When it comes to capacitors, those are the two most common, is microfarads and picofarads. There's also nanofarads, which is right in the middle. I will say that's kind of a newer, it's not a newer term, but it's a newer way of rating capacitors. In the old days, it was either microfarads or picofarads, one or the other. Picofarads, PF, often is called puff, so you might say that this is a 10 puff capacitor. I've heard that terminology. And if you're talking microfarads, generally you're talking bigger electrolytic capacitors. If you're talking picofarads, you're usually talking like little disc capacitors, ceramic capacitors, mica capacitors. So what do I mean when I say electrolytic, disc, ceramic, mica? It refers to the dielectric inside the capacitor. Capacitors are one of these interesting devices where there's a huge array, kind of like breeds of dogs. You get little Chihuahuas versus St. Bernards versus sheepdogs. There's vast differences, and you'd hardly recognize a Chihuahua compared to a sheepdog, but they're all canines. Same with capacitors. So these capacitors have inside a big, huge coil of aluminum and usually a paper insulator. And there's a somewhat liquidy material called an electrolyte. So that's why the full name is aluminum electrolytic capacitor, because they have aluminum foil and paper and then an electrolyte. So they're not wet in the sense that liquid's going to pour out of it, at least you hope not. But they do have a chemical inside. And that's actually usually the failure mode on these capacitors, is that electrolyte leaks out or is boiled out. But the advantage is they have very high capacitance values. These are film capacitors. This is probably polyester. So inside there's something similar to this, only they're dry. There's no liquid electrolyte. And there's a polyester insulator, and then some kind of a conductive material that often is applied right onto the polyester strip. These are much smaller in capacity, but they're often rated for higher voltages. Actually, all these components right here, I picked these in particular because these are all the same capacity. They're all, forgetting what capacity they are. You have to decode the writing on them sometimes, but I had them all in the same envelope in my parts cabinet. Here we go. They're point. Yep, there we go. They're 0.1 microfarad. 0.1 microfarad. But they differ in their voltage rating. They also can differ in how stable they are at various temperatures. If you put it in a rig that's going to get warm as it operates, some of these capacitors can have a huge change in capacitance. And if they're in a tuned circuit, that's a big problem. Versus in a power supply where you're just filtering, the capacitance really doesn't matter how much it changes as long as it's within certain pretty broad range. So that's why there's just such a variety of capacitors. So if a capacitor allows AC to flow but blocks DC, an inductor blocks AC and allows DC to flow. Now it's not perfect. That's why, again, there's different values of inductors. But in general, inductors are chosen because you want to pass direct current or block alternating current in some way. Now, all inductors have resistance. In fact, all these components exhibit all of these characteristics to some degree. A resistor has inductance. An inductor has resistance. Usually those other characteristics are negligible in the circuit, but you do have to keep that in mind because that resistance may still be a problem, or at least may need to be accounted for if you're using this to pass direct current. Different values of inductors will pass AC or DC at varying amounts. So all inductors pass direct current to some extent, some better than others, and they all oppose AC to some extent. Again, some better than others, or some better at different frequencies. And they are measured in henries. And while we're on that slide, I'm going to go back to resistors a little bit because resistors can be made in different ways as well. This resistor here, I just know by its shape and construction that this is a carbon composition resistor. So inside of this plastic or bakelite housing is a bunch of carbon that's just packed really tightly together with terminals on each end. So this has almost no inductance. The inductance of this part is negligible. It truly is as close to a perfect resistor as you can get. Whereas this right here is a wire-wound resistor. This is called wire-wound because inside of this ceramic housing literally is a piece of resistive wire that's wound round and round and round some kind of a form. Well, this starts to look like this or this. That coil of wire is an inductor. In fact, you can make inductors, practical inductors, by literally coiling a piece of wire. And so these wire-wound resistors have very high inductance. But that's usually not why you select them. You select this for its resistive properties. But as a side effect, you get inductance. So you just have to be careful when you're working with a circuit that you choose the component that makes the most sense. If you're working in a tuned circuit, you wouldn't want to use a wire-wound resistor because you want to specify the inductance and capture that using an actual inductor that has a specified value. So in a tuned circuit, you might go with a carbon comp resistor, or its close cousin here is a carbon film resistor, very similar construction. But in a power circuit, especially a direct current, doesn't matter. Use this wire-wound resistor. The advantage is this can carry a lot more current. If you're working with a tuned circuit, you're probably not carrying a lot of current. You're probably making a little oscillator, and the amount of current flowing through that circuit and that oscillator is negligible. It's important. You want current flow, but it's just not much. You just don't need much current. Whereas if you're dropping direct current to operate an incandescent light bulb, for instance, you're dropping a tremendous amount of current. So you need a resistor that can carry that kind of current. So,
Your fingers on those.
yes.
Touch it, I sort of know it anyway.
Yep, and they're made so they can run hot and it's not a problem. These, if they get hot, they can burn out. Or at best, their resistance value will change, and then that changes the properties of the circuit that they're in. I kind of skipped over what inductors look like. I talked about it a little bit, but these are all inductors that I just found in my junk box. Like I said, a coil of wire like this can be an inductor. These two here are actually variable inductors. There's a little ferrite core inside, and you can adjust that core up and down, and that slightly varies the properties of this inductor. So if you're using this in a tuned circuit, you can get that circuit peaked right to the frequency that you want it to oscillate at.
You ever had a little Christmas, you tune that inductor with that core in there to that radio station frequency that you want to try and listen to?
Mm-hmm.
First radio was a little Christmas set. I should have brought that along.
Yeah. Diodes are simple little one-way gates. Current can flow one way and not the other. Sometimes you have a device that has two power sources. Either you can plug it into the wall or you can run it off from battery. So you might have a diode on each of those sources, so it doesn't matter which source you choose. You don't want the wall circuit to backfeed the battery because we just talked about batteries, they can't all be charged. Or you don't want the battery to try to backfeed the wall outlet either. So they might have a diode on each of those so that it doesn't matter which one you use, the device still is powered. Or if you want to convert alternating current to direct current, we'll talk about rectifiers coming up here. Yep. So there's usually, yes. If you use a center tapped transformer, you can get by with 2 diodes. But if you just use a regular transformer, then you need 4 for a bridge rectifier. Or if you just want a simple, we call it a half-wave rectifier, 1 diode is all you need. So if you have an alternating current source and you run it through a single diode, you'll only get the 1/2 of that oscillation. So you might get half of an oscillation and then nothing, and then half of an oscillation and then nothing. Now, that's rarely a useful signal, so then you run that into a little filter cap, and the filter cap can make up for those ups and downs, but still a half-wave rectifier is still very rough. It requires a lot more filtering. In fact, if you see some of the cheaper LED Christmas lights, especially if you're driving by them, you can see them actually flickering because they just have half-wave rectifiers and no filtering in that circuit. Whereas a bridge rectifier will take the top hump and pass it, then it takes the bottom hump and passes it as DC, and the top hump again is passed, and so you get a much smoother output. What you get is hump, hump, hump. If you looked at it on an oscilloscope, there's no gap in voltage. There's just the ups and downs of the oscillations. So all the oscillations on the bottom of the original sine wave are now flipped up to the top. So it still takes some filtering. And you can also do that filtering with inductors. Usually they're a lot bigger than this. But especially in vacuum tube equipment, you might have a full wave rectifier, but then that goes into an inductor. Usually it's a big choke. That's what they're called. And then a little bit of capacitance. Especially in the older days, these big high-value capacitors just weren't practical. And so you take a combination of a big choke and a capacitor to get smooth DC in the circuit that you're using. Some diodes have this special property where they emit light. We have an example coming up. There we go. Larry's got one. Yeah. So diodes allow power to go in one direction and not the other. With LEDs, if you have power going in the forward direction, they produce light. If you have power attempting to flow in the reverse direction, they're just shut off. They don't pass much current, or at least you don't want them to. So, usually you'll put them in series with the resistor to limit how much current flows through them. Now, all diodes have voltage drop. I don't know if that's, go to the next slide if you would. Oh, and I'm sorry, here it is right here. It says most silicon diodes, which is what this is a silicon diode. Most silicon diodes have a small voltage drop of about 0.7 volts. I'll say in practice it's 0.6 to 1 volt, roughly. So if you have current flowing in the positive direction, in this case, it actually doesn't matter too much how much current flows. It will drop that 0.6 volts, 0.7 volts, pretty much no matter what. LEDs happen to have a much higher forward voltage drop. Usually it's 2 to 3 volts at least. Some of the high-powered ones might be 3.5 volts of drop. So you just have to keep that in mind in the circuit that you're using it. So in my earlier example of a device that has 2 power sources, if you have one of your sources is a 1.5 volt battery, and you're using a diode as a gate, you're losing 0.7 out of that 1.5 volts, and that's usually not acceptable. So the amount of voltage drop on a diode, it can be a problem for a circuit. Even in a let's say you have a 12 volt mobile rig, and you've got a battery and a power supply, and you're doing the same thing, that 0.6 volts, it can be a problem. Let's say you got a lead acid battery, and you don't want to drop that below 11.5 volts, for instance, and your radio wants 11.8 volts, and you're going through a diode that's losing 0.7 volts, you can't use much capacity out of that battery in that sense. So just something to keep in mind, that voltage drop can be a problem. Yep, we covered LEDs. They're indicators. These are LED lights. There's so many uses for light emitting diodes now.
Sometimes their power supplies make lots of noises on radios.
Yeah. While we're here, I'll talk about the schematic symbol a little bit, so I kind of glossed over that. If you look at the symbol, it looks like an arrow pointing to a wall. This is really helpful because that arrow shows you what direction the power flows. Now I'm going to go on a tangent because I can't let this go without talking about which direction do the electrons actually flow. In all of our practical applications, it's usually best to assume that the positive terminal is the source of the electrons and they return to the negative terminal. That's called conventional theory, I believe is what that's actually called, conventional theory. And that's how we've always been taught since school. And it's so common that in a practical sense we still look at current flowing that way, but that's wrong. Electron theory says that the current actually flows from what we call the negative through the circuit and back to the positive. If you've ever used vacuum tubes, you know that right away. And I'll talk about these a little bit more later. These are not in the book, so I'll cover these at the end. But from a practical sense, that is not a big deal. But current does flow from negative to positive. We just forget about that. I shouldn't have gone down that rabbit trail. That's not in the book, but I had to mention it.
The other thing I mentioned on diodes too, just from a practical standpoint, or LEDs rather, like all diodes, they have a plus, minus, and a positive. A lot of times they'll have either a line on the LED or a straight side on one of them, and that's typically the negative side. They need that resistor that Nelson talked about. I think I gave you 220 ohm for that current stabilization. And then usually the longer, they have 2 different lengths of leads if they're new, if you take them out of circuit, but sometimes you don't know. But they'll often have one will be a longer lead, and again, that'll be the positive lead, and with the shorter one will be the negative lead.
Good. And I'm glad you brought that up because I kind of forgot to mention that in some of these components. Some components have a polarity. Even if they're not designed as a diode, you still want to put power to them in a certain way. Resistors usually don't care. In fact, I can't think of any resistor that has a polarity. But capacitors often do, especially electrolytics. Electrolytics almost always do. Not always. But like this one's got a big stripe down the side with little minus symbols, so that's the negative side of the circuit. When you're using this, that always has to be lower in voltage than the other side. The results, if you get this backwards, can be spectacular. That's right. And so you'll see either the stripe on the side or different components have different ways of marking what the positive and negative side is. If you really want to get picky, and this is more of an older radio thing, but even these film capacitors, these don't care what polarity they're used, but there's an outside film in a spiral, and then there's an inside connection. And so sometimes, if you really want to be picky, you'll actually want to figure out which terminal, which lead goes to the outside foil, and that'll be your ground side. That helps to reduce how much noise is picked up in this capacitor from other parts of the circuit. That's a pretty specific example, but it is a case where polarity kind of can matter. Series and parallel, I think we've pretty much covered that. One thing I want to mention briefly is on this battery symbol. I don't think the book specifically said this, but on the battery symbol, it's got alternating plates like this. The larger line in that symbol is the positive terminal of the battery. And also, if there's only two plates, if you only have a big line and a little line down here, that usually indicates a single cell source, a single device. If there's multiple lines, it means it's a multi-cell battery. I don't know if people always remember that, so that you can't always count on that in a schematic, but from a theoretical sense, that is how that symbol is supposed to be used. You could also argue, if it's only one cell, is it truly a battery? A battery, like in the military sense, is several weapons, not just a single one. But that's because in the old days, or at least the early days of electronics, you often would have several of these cells connected together. Even for a flashlight, they didn't sell cells individual. They'd have 2 or 3 pre-assembled in a cardboard tube, even for a flashlight. And that's where that term battery came from, because it was a battery of cells.
I mean, even the AA's, a lot of them are multiple cells.
9 volts are, for sure, because they're 9 volts. Even the little ones that you'd put in a garage door opener, often they're 12 volts. So they're 9 individual tiny cells in one package.
Was there anything else there, Nelson, you did?
How about anything for you?
No, I think we covered that, so.
So, summary.
Looked at all those.
I don't think the test goes into as much detail as calculating the value of series components and parallel components, but that is something that in a practical sense, it is good to learn. Let's say that you need a 5K resistor. You look through your parts and you don't have a 5K resistor. So what resistors can you put together to make 5K? You could take 5 1K resistors and put them all in series, and that'll give you a 5K resistor. Well, let's say you need a 5 microfarad capacitor. Do you take 5 1 microfarad capacitors and put them in series? You put them in parallel. It's all those things you just kind of have to study and learn.
Yeah. Stupid question.
Mhm.
Why are there 3 leads on the potentiometer?
Good question. In the basic sense, a variable resistor would only have 2 leads. And some devices, they're often called rheostats if they only have 2 leads. They truly are just a coil of wire, terminal at one end, and a variable tab that wipes back and forth on that resistive element. But quite often, in a practical sense, in a circuit,
That's called a wiper?
yep,
Yeah.
And this, so this is the increasing resistance. So if you think of this as a resistance wire, it means a material that increases resistance as you go around. So as you turn the center, you decrease it to 0. You can get 4 resistance by putting 2 leads here, or you can do 2 here. Sometimes you want to decrease something while you're increasing something else.
mhm.
Okay, so it just gives it more functionality for you.
Well, and I'll talk in a practical sense here about how these are often used. Take a volume control, for instance. Remember how I said that resistors limit current but not voltage? But yet, in your circuit, when you're going into the final stages of an audio amplifier, you need a voltage going into that amplifier. And so if you put... Nope, actually, this is fine. Thank you, though. I just want to make sure Michael can see. Okay. If you put a voltage here on this side of the resistive element and you ground the other side, then you've created a device called a voltage divider. What that does is that sets up a fixed current through this device. And so as you move that wiper, now you have a variable voltage depending on where you move that wiper across this circuit. But it takes 3 terminals to do it because you have your voltage on one side and you have a ground reference on the other side. If you eliminated this and you just had a rheostat, you put a voltage here, if the input state of the amplifier doesn't draw much current, moving this wiper doesn't really do anything. Because even way over here at full resistance, because there's so little current flowing through the circuit, this resistance is negligible and you don't get the variable gain effect that you want. But that principle right here is common throughout all kinds of different circuits where you're using this to vary the gain of a circuit. And so to set that gain, to get the voltage that you want, you have to set the current to something that's known. And you do that usually by grounding one side of that resistive element. Transistors. These are the components that are usually found inside of an integrated circuit. But a transistor in the simplest sense, these are examples of transistors here, they're valves. With a basic transistor, a small voltage applied to one terminal allows you to control a larger voltage on the other. Now that's an oversimplification, but that's the basic principle. And you can use that in a lot of ways. But if you can use a small signal to control a larger signal, well, now you can make an amplifier. Let's say that you've got a microphone which produces a very tiny little signal, but you want it to connect to a speaker that a large number of people can hear. You could take a big power source. Let's say this is a big, beefy power transformer. You can take a big power source, run it through that transistor, and then the small signal that your microphone creates allows the transistor to turn on and off in step with the voltage that's being applied to it to control that larger voltage being applied to the speaker. Now that's greatly oversimplified, but that's the basic principle behind a transistor in the sense of an amplifier.
It's kind of like a logic gate almost.
Sort of, yeah. I'm sure I'm covering all of this. There's several different types of transistors. Let's go to the next slide because I want to talk about bipolar transistors and field effect transistors. So before I get to that, using our water analogy, this is kind of a neat drawing they have because they have a little tiny waterway here and a big water source over here. And a little bit of water flow here moves the gate to allow this big water source to flow. And transistors have what's called a linear region where within certain limits, the voltage or current that you apply through that transistor allows it to variably open and close that big gate, for instance, in step with the small signal. So let's say, just for sake of argument, that if you apply between 0 and 1 volt to the control pin of this transistor, you could control a larger voltage. Let's say it's 100 volts. So a half a volt here might give you 50 volts on the output. A quarter of a volt might give you 25 volts on the output. It's linear or close to it. But there's limits. So if you applied, let's say, 1.5 volts here, well, the transistor is already fully open. It can't open any more than fully open. So you're still only going to get that 100 volts on the output no matter how high the voltage goes on the input side. So that's exceeding its limits. Now I've been interchanging voltage and current a little bit here in my discussion. On the next slide, it'll probably talk about, here we go. The two most common transistor types are the bipolar junction transistor, or bipolar transistor for short. That's what this is. And the field effect transistor. I don't have one handy. You can't always tell them apart by appearance anyways. Often they can be sold in the same packages. But the big difference is that bipolar transistors, they vary the gain based on current on the input side. So you have to have a little bit of current flowing between the base and emitter to control the amount of current that flows between the collector and the emitter. Whereas with field effect transistors, they rely on an electric field produced by a voltage. And I'm picking my words out carefully because that should help you remember the difference. If you just have voltage, you have an electric field, you don't have current flow. So a field effect transistor varies the flow of electrons based on the strength of the field that's created by the voltage that you're applying to the gate, or it's between the gate and the drain. That's the terminology used for a field effect transistor. So a small voltage between gate and drain allows for a large current to flow between source and drain. Which one you choose is based on the characteristics of the circuit. If your circuit is going to have a small current flow, then use a bipolar. If it only has a voltage, then use a field effect transistor. Again, that's oversimplifying things, but that's the basics. That's enough that you need to know for the test. And let's go to the next slide and see if it talks about PNP and NPN. Larry talked about, it doesn't, but that's okay. I'll touch briefly, very briefly on this. There are also,
Actually, the slide before talked a little bit about the three areas, three regions of semiconductor, which has to do with PNP and NPN. I don't know if that helps, but probably doesn't help too much further.
that's okay, it's not on the test anyways. I don't think it's until you get to extra class that you have to know the difference. But suffice it to say, in a very simple sense, there are PNP and NPN. And it refers to how the layers of conductive material are arranged inside the package of the transistor. And in a very simple sense, one is positive and one is negative. So if you're working with negative voltages, you use one. If you're working with positive voltages, you use the other. If you're working with both, sometimes you use them both, PNPs and NPNs. Usually, in a practical sense, transistors are sold with complementary PNP and NPN components. So a 2N3902 is a partner to a 2N3904. One's PNP and one's NPN. And while we're talking about transistors, I'm going to deviate from the book. This is not in the book or in the test, but I can't pass up the chance to talk about vacuum tubes. Now, in the United States, we call these vacuum tubes. The rest of the world calls them valves, because that really is a better description of what these are. These are like field effect transistors with pilot lights. You put them in a circuit and they glow. They glow kind of a dull orange, even a bright white, depending on what's inside, because they rely on the heat of a filament or a heater to cause electrons to flow inside this glass envelope. We call them vacuum tubes because we've evacuated all the air from the inside. Before transistors, these are what we used. And in many cases, I bring them up because they are still used. Because in general, these are more durable and can handle higher powers and often can handle higher frequencies than transistors. Not so much the case anymore because transistor technology has gone so far. But they still have a role. Whether you're working on older equipment or high power equipment, you're still likely to find tubes. The pro audio guys also like them too because they can have a little bit cleaner sound, but also if you operate them outside of their linear region, their distortion is a little more pleasing to listen to in an audio sense. So I got to bring that up. And just like with transistors, there's thousands of different kinds of tubes optimized for different parts of a circuit. Now this tube is actually not an amplifier. It's not like a transistor. This is like a diode. In fact, this is a dual diode. This is designed specifically to use in a power supply of a radio, where if you have a center tap transformer, so you have a high leg, a neutral, and a low leg, for instance, and two diodes, which just has two diodes in one envelope, you can make a full wave rectifier. But this is just like having two of these devices in circuit. Whereas both of these are triodes. Triode meaning there's three basic elements. You have a cathode, a grid, and a plate. And that's roughly equivalent to the three terminals, the gate, source, and drain, that you'll see on a field effect transistor. Vacuum tubes allow a small voltage to control a large current. So if you apply a small varying AC voltage between the grid and the cathode, that controls the flow of electrons between the cathode and the plate. So in a circuit, you set up a voltage that causes a current to flow from the plate to the cathode in a circuit. The voltage on the grid can interrupt that current flow, where you can create an oscillator or an amplifier, just like you would with a transistor. So I grabbed this one. We can look at these afterward. I just grabbed this out of my junk box because it's really easy to see inside, and you can actually see all those parts inside the tube. Whereas with the transistor, you can't physically see those parts without a laboratory equipment. This is a real common one. The pro audio guys go nuts over these. This is a 12AX7. It's a dual triode. It's like having two of these in a circuit. You could have two amplifiers with this. You could daisy chain one to the next so you get greater amplification, or if you had a stereo system, you have a left channel and a right channel. But this is a real common audio preamplifier. I just had to mention that because you will encounter tubes. Now, talking about measuring voltages, I said that you can have high voltages on a tube. Just because of how thin all the structures are inside this tube, they don't usually carry a lot of current, but they can handle a high voltage. So it doesn't matter whether you have high voltage, low current, or large current, small voltage, you can still get a lot of power out of a circuit. It's like a balance. You can have a lot of current or a lot of voltage to get a high amount of power. And in the end, what you really want is power. So these work on the principle of really high voltage. So if you put, this might only take 300 volts on the plate, but if you put 300 volts between the plate and cathode, that's still a pretty high voltage. But then you can transform that, and we'll talk about transformers shortly, you can transform that into a lower voltage, higher current to do work for you. That makes sense? Transistors, tubes, etc. Because now we're going to move on to a few other components. We talked about light emitting diodes, but they have a different schematic symbol if you're talking about a regular light bulb, an incandescent light bulb. That symbol is on screen, it's in your book. Incandescent light bulbs have an interesting property where they are self-limiting. Now with an LED, once you apply enough voltage to get over that forward voltage drop, let's say for an LED it's 3 volts. If you apply 3 volts or more, now all of a sudden that device just turns on. That gate opens up, and it opens full open. And more current will flow through that device than what you really want it to, so you have to limit that with a resistor. With an incandescent light bulb, the hotter the filament gets, the more resistive it gets, so it self-regulates. That's one of those basic things that nobody ever explained to me, and I just had to discover it later in life, that it really is self-ballasting. If you measure the resistance of a cold incandescent bulb, it's very low. It might be less than 1 ohm of resistance. If you do the math, you might say, oh geez, 20 amps of current can flow through that bulb. And in truth it does, very briefly, until that filament gets hot. And once it gets hot, its resistance gets much, much higher. We talked about the symbol line, the symbol with the lines for batteries. An antenna symbol's up there on the board. Fuse, we talked about fuses earlier. They're electricity safety valve. Fuses, I should have brought some fuses to show too. There's different types of fuses, and usually you rate them by their voltage, how much voltage you can pass through the fuse, but you also rate them by how fast they blow. So a 10 amp fuse, if you put 11 amps across it, usually doesn't open right away. It can handle 11 amps for a long period of time, even a 10 amp fuse. It might be several hours, it might be a day. It'll allow 11 amps to pass. If you put 15 amps across it, you might only allow that for a few minutes. If you put 200 amps across it, it's going to blow right away. Well, it's going to blow within a few milliseconds. But even that is a length of time. And that still might be enough time to do damage in a circuit. So if you're putting a fuse in a circuit that's got a capacitor or an incandescent light bulb that can handle a whole lot of current when you first plug it in, you might choose a slow blow fuse, one that opens a little bit slower. But if you're talking about a very sensitive circuit inside a device with some transistors and such, you might want a very fast acting fuse that opens right away. Meters, we talked about meters. You can have meters like this built into a device. Regulators, this is actually a regulator here. This is an LM317. It's a very common 3-terminal voltage regulator. By the resistors that you hook up to this device, you can set how much voltage you get out of this device. And so let's say you have a device that you need it to have 5 volts. And it will not operate properly if it's very much higher or lower than 5 volts. But you can't rely on your battery providing exactly 5 volts. Maybe you've got a 12-volt battery. So you set this up so that no matter what the input voltage is, within a certain range, it drops it down to 5 volts.
So Arduinos and Raspberry Pis will often have a regulator like that on them, so you can just plug in 6 to 12 volts or something.
Sure.
And get their 5 volts and they're happy.
Or if you are using a common voltage like 5 volts, 12 volts, they make specific versions of those that are already set to that voltage. Like an LM7805 gives you 5 volts. An LM7812 gives you 12 volts. 7905 gives you negative 5 volts. 7912 gives you negative 12 volts. So those are all various integrated circuits that I mention those because those are real common. Probably half the things I build, I'm using one of those, we call them jelly bean components because they're just so common. They're standardized. Transformers. These are massively important, and I'm surprised that you only get one mention in the book. But a transformer it's an inductor of sense, but it's got 2 coils, or at least 2 coils inside, and they're coupled magnetically to each other. So this is a good example where you can see this coil. This is a big coil of wire all wrapped around itself, insulated wire. And here's a coil of wire all wrapped around itself. And they share this magnetic core. So if you pass current through one of these coils, doesn't matter which one, it'll create a magnetic field, and as that magnetic field passes through the other coil, it induces a voltage in the other coil. But if you change the number of turns, let's say you have 10 turns on one side and 100 turns on the other side, if you put 10 volts AC into that one side with 10 turns, while the side with 100 turns is going to give you 100 volts out. So it's a very simple way to transform alternating currents. Only works for AC. So this, I wrote it here with the pencil, this came out of a product.
Just the opposite is true.
Yes, thank you.
So if you have high voltage, you can step down. In fact, we call them step up and step down transformers depending whether it increases or decreases the voltage.
Yep, and that terminology is based on how you're using it, more so than the characteristics of the transformer.
You could reverse it and do the opposite.
Right. So within certain voltage limits, again, you can't exceed the voltage that would cause this to arc over. But it doesn't really matter how much voltage you put into one side, you'll get 1/10 or 10 times, depending on which direction you use it. And the voltage source is connected to the primary coil, and then the secondary coil goes to the load. Again, that's more of a mnemonic in the product. So this transformer right here doesn't care which side is the primary and which side is the secondary. It'll transform up or down depending on how you connect it.
Sometimes you'll even have taps in a transformer. So going back to Nelson's tube example, you might have a filament voltage of 6 volts or something, but then you may have a higher voltage for other aspects of the circuit or the tubes. And so there's multiple connections, and then similarly, multiple numbers of wraps that you tap off of to get the voltage you want.
Okay.
Yep. Oh yeah, so you'll see one of these, they might have 12 wires sticking out of it. And
Each of them corresponds to that.
yeah, and usually they're color-coded, but I hope you have the data sheet that came with it, or it's hard to tell what's what. There's a transformer symbol, and the symbol looks a lot like two inductors close together because that's truly what it is. In fact, sometimes, especially if you're prototyping, you may only use one coil, and you use that coil as an inductor, and you just leave the other side disconnected. All right, switches. You have to know this terminology for the test. So I brought some old knife switches because it's really easy to understand these these terms if you can see them set up like this. So a basic light switch is on and off. You have one pole, you have one blade here, and you can only throw it one way or to one contact. So this is a single pole, single throw switch. This switch, you can move. This, you still only have one blade, but you can move it two different directions. So that's a single pole, double throw switch. Now this one has two different blades that are insulated from each other, so that's a double pole. This happens to be a double throw switch. You could also have a double pole, single throw switch. You can have as many poles as you need. You usually only have single throw and double throw. But it is important to understand that terminology for the test, and always have different practical applications. Maybe this is an antenna switch. You got two different antennas. You connect your radio to the middle terminals, and you connect the two leads off to this antenna and two leads off to this antenna, and depending on which one you want to use, you can just switch back and forth. Or Michael's got a case where he's got two different power sources for his shack. So he can switch it one way for utility power and another way for solar power. Real common. But it's common to have these switches packaged into very small devices and used inside a radio. And you just have to look at the terminals on the back of the switch to figure out what kind of switch it is. A power switch is usually just a single pole, single throw switch. But let's say that there's a couple different things being switched on and off when you turn that switch on. So maybe you actually have a double pole, single throw power switch. Just some examples. A relay is a type of a switch that's controlled by a current. In some ways, that kind of sounds like a transistor, doesn't it? Where you have a small voltage controlling a larger current. Truly, there's a lot of overlap between transistors and relays, and some transistors can be used as relays. The big difference is relays are on or off, and usually they're controlling higher currents. So with the relay, you've got a solenoid, big coil of wire, and something that can move, and it's physically opening and closing that switch for you. Usually there's a set of contacts that's opening and closing inside the relay. But even relays can have multiple poles and multiple throws. We talked about rectifiers already. It's an implementation of diodes in a circuit. Converts AC to DC. Real common. Larry talked about having a crystal radio. A crystal radio is really a tuned circuit and something to convert that AC signal into DC that goes to your headphones. That's all a crystal radio is. But a tuned circuit uses a combination of capacitors and inductors. If one device allows AC to flow and one device restricts it, and you balance those two just right, you can tune a circuit to a certain peak frequency, but in practice it usually has some bandwidth to it. Now this is not in the book, but that bandwidth that I mentioned is called the Q of a tuned circuit. So a very high Q circuit is very narrow. It might only pass 146 megahertz with very little above or below that, whereas a low Q circuit might pass a pretty broad range of AC frequencies. Depending on what you want, I'm not saying one circuit is better or worse, it just depends on how you want to use it. If you're trying to pass the entire 2-meter band into your receiver so you can tune across it, then you want a really low Q, broad tuned circuit. You're just trying to filter out stuff that's outside of the 2-meter band. But if you're actually trying to listen to a station, then you want a very high Q circuit that just picks up that station that you're listening to. The response voltage by frequency of the tuned circuit. The voltage is greatest at the frequency of resonance. So at the peak, at whatever that circuit is tuned for, that's called its resonant frequency. And the voltage through that circuit is greatest at that resonant frequency, and it falls off on either side. Yep. So this is showing current flow. So you have a current source here through a resistor that helps to create the right current flow through the base of the transistor to the emitter to ground. And now you have a voltage source over here. It's a multi-cell battery going through a light bulb, and it's connected to the collector of this transistor, and then current will flow through the collector, through the transistor, out the emitter when you have a voltage being applied to the base. So that's where you might take a very small signal through a potentiometer. If you were to actually power an incandescent light bulb, you'd need a pretty big potentiometer because they draw a lot of current relative to how much a little potentiometer like this can handle. But if you're just using this to generate a small current to go through this transistor, the transistor can handle the higher current that's needed to light that light bulb. We will cover soldering in the next section.
You might just show that. I don't know if we have a cold solder joint, but it's just a good picture of a bad electrical connection there.
Yep. Do you have any experience welding?
No.
Okay.
But I know it's supposed to be like nice and smooth.
Yeah. You can use the solder and lump it onto the component, but if it doesn't really adhere to the component, it doesn't make a good connection. Or like with welding, if you're welding two pieces of steel together and you don't get good penetration, if you're not melting those base metals sufficiently, and you get all done, it doesn't have any strength to it. This is just showing you various components. There is test questions where they'll show you pictures of a circuit like this, and they want you to identify the components. So just review this in your book.
So the blue ones are the ones that are in the pool and could be asked. So.
Mm-hmm. This is actually an interesting circuit. Normally in schematics, you work left to right. So if you have an antenna on one side and a receiver, so a receiver has an antenna on one side, amplifier stage, a filter stage, a detector stage, and an audio amp stage. Usually they're shown left to right on the schematic. This is actually backwards. This is showing a voltage source on the right. This Zener diode is acting like a voltage regulator. This is then allowing you to vary that voltage. This gives you a LED. You have a capacitor, a diode. Actually, they have the diode going the other direction, so this isn't really a practical circuit. But then they're transforming this up to a higher voltage to light a neon lamp, I guess is. But you don't have to know what the circuit does. That's beyond the scope of this class. They just want you to identify the components.
Anybody use neon lights anymore?
I tell you what, here's another application of a neon bulb. Originally they were used as indicators. Well, wait a minute.
They just lived. They didn't burn out. The filament didn't burn out like a traditional. Oh yeah, there.
This one either doesn't have one or it's burned out. Or it's LEDs do have at some point they get exhausted, but they're indicators and they're really cheap. But like an LED, you have to put a series resistor with them because once you exceed the breakdown voltage, they're wide open. They'll blow up in your face if you don't have a limiting resistor. Ask me how I know. But now here's an application of that. If you have a voltage source and a current limiting resistor and some capacitance in your circuit with the neon bulb, once enough voltage builds up in that capacitor to exceed we call it the breakdown voltage of that neon bulb, it causes the neon bulb to light. Once it lights, so it draws current, and it drops the voltage in that capacitor, and current stops flowing. Voltage builds back up in the capacitor, and the light turns on again. Well, that's an oscillator. You can build a really crude oscillator with a neon bulb and a capacitor and a resistor.
Our house is just over 20 years old. We bought it about 5 years ago, and it still has some switches in the house, especially the bedroom, that have neon lamp indicators, just so you can find the switch, not that it does anything. And they're still burning solid after 20 years.
Yeah.
It's just incredible that neon bulb can last 20 years.
Oh, yeah, I've seen those before. They're the little slightly flickery ones.
Yeah,
Yep.
it's a nice flicker. These are pretty steady. In fact, they're behind the plastic. You can't even see them, but it lights up the plastic, and they're orange, so you know they're neon. And they're 20 years old, so.
That's it. Any questions? I forgot to show these too. These are little ferrite cores. Ferrite's just a type of a powdered iron that's formed together. These by themselves aren't very useful, but if you take small magnet wire, you wrap it through these number of times, and you can build a device or a component with the inductance that you need.
Oh, okay.
So it's not unusual to wind your own ferrite inductor, because you might need a very particular inductance for a tuned circuit, and you literally wind it with wire. I've got a whole cabinet full of these. These come in different values too. The values based on the size, but also the mix of that iron powder that's in that ferrite. So it's pretty common to use those and build your own. Oh, I didn't cover crystals either. This is not in the book or on the test, but this is used in an oscillator circuit. A crystal helps a tuned circuit be on a certain frequency.
Yeah, they vibrate at a certain frequency
Yeah.
when you run electricity across them.
Yep. Crystals are still real common now. In the old days, especially like on FM, you'd have to get a crystal for every channel that you wanted to use in your radio. So if you wanted the East Jordan repeater and the Petoskey repeater and the Mancelona repeater, you had to get crystal sets, transmit and receive, for each of those frequency pairs. But even nowadays with synthesized radios that you don't need crystals in that sense, you see crystals all the time in tuned circuits because they offer a very stable frequency source to keep that circuit.
Crystal to get the exact frequency.
I never have you?
I haven't. I thought I've seen it done. I said I'd like to try that sometime.
Yep.
I was watching a YouTube video. They were talking about quartz crystals for watches and how they use that along with they call them flip flops, but to turn that very high frequency to a lower frequency, right?
Divide it down to something more useful.
Yeah.
Yeah.
So
I think we should solder them.
All right, let's do.